Okay, so let's take on multiply connected domains. Section 49, 4.49, multiply connected domains. We're looking, well, we'll see something that's kind of Cauchy-Gersau-esque in this section. We'll see integrals which are zeros, and the proof will be based on the Cauchy-Gersau theorem. Remember, Cauchy-Gersau says simple closed contour, function analytic on and interior to that contour implies integrals are zero. So integrals of analytic functions in the appropriate places will be zero. Okay. We'll define a multiply connected domain as one that's not simply connected. So let's go back and take a look at the pictures we had in the previous section for simply connected and not simply connected. The definition of simply connected was every simple closed contour in the domain encloses only points in D. So if I draw some little simple closed curve, don't let it intersect itself. It starts and stops at the same place. That has inside it only, in both of these, only points that are yellow, only points in the domain. Over here, we could take a contour that went around the hole in this annulus, and in that simple closed contour would have interior to it points that aren't yellow, points that aren't in the domain. Over here, we could go around one of these little holes that's been punched in the domain, or for that matter, go around more than one of them. And inside that simple closed contour, we would have points that aren't yellow, points that aren't in the domain. So that's the idea behind multiply connected. So multiply connected means not simply connected, to give you a more straightforward definition instead of not simply connected. Domain D is multiply connected if there's a simple closed contour in D that encloses points that are not in D. They're in the complement of D. And that was the idea. Go around one of those little holes that have been punched in a not simply connected domain. You get interior to such simple closed contours, points not in the domain, points that aren't yellow in the pictures that we had. Okay, so here's a result, theorem 4.49.a. It's about an integral that equals zero, or a bunch of integrals that sum to zero. The statement is this. Let C be a simple closed contour parameterized in the counterclockwise direction. Excellent. Usual kind of thing. All right, now what we're going to have is inside that contour C, a bunch of little contours. We'll look at a picture and it'll make sense once we see the picture. Let's read through this math stuff first. Let C sub k, for k equals 1 to n, be simple closed contours interior to the big contour C. All of these parameterized clockwise, parameterized in the negative direction if you like. These are disjoint and their interiors have no points in common. So the contours don't intersect and you don't have one of the contours inside the other. Yet they're all inside this big contour C that we started with. C is parameterized counterclockwise and the little c sub k is parameterized clockwise. It's opposite orientations in a sense. If function f is analytic on all these contours and throughout, get this, the multiply connected domain consisting of all points inside C and exterior to the c sub k's, then the integral over c of f of z plus the integral over each of those c sub k's summed from 1 to n of f of dz dz equals 0. Okay, here's what that really means. Okay, so if we get a picture, we should be in pretty good shape. Let's zoom ahead to the picture. So here's what they're getting at. Figure 60 gives us a contour C. All right, it's parameterized in the positive direction, in the counterclockwise direction. Inside it is a little c sub 1 that's parameterized in a clockwise direction, a little c sub 2 that's parameterized in a clockwise direction, and so forth. So there were, I guess there were n, wasn't it? N of these little c sub k's but I don't have one of the C sub k's inside another one, was part of the rules. And we don't have these C sub k's intersecting. Okay, so counterclockwise on the outside, inside, several disjoint, little clockwise oriented simple closed contours. And they said F was analytic on each of these contours and in the multiply connected region that's inside C and outside C sub 1 and C sub 2 in this picture. So they're saying F is analytic kind of in this little figure 8 that's enclosed by C, and you're allowed to go through and remove the points inside C sub 1 and inside C sub 2 and so forth. So you're punching holes in the region of analyticity. You're punching a hole, it's the interior of C sub 1, the interior of C sub 2, and the interiors of the other subscripted Cs. All right, and we'll go through the proof, and what they're doing is they're introducing some line segments and setting up integrals and ultimately using Cauchy-Gier's thought. All right, so we've got the statement. We're making some assumptions that are geometrically very plausible. And I'll make a comment after we get through the proof of this, how we could back this up with something a little bit more rigorously. But what we're going to do is introduce polygonal law in L1, consisting of a finite number of line segments joined end to end to connect the outer contour C to the first inner contour, C sub 1. There it is. So what they're doing is they're going from this point, they're putting a line segment or a sequence of line segments, polygonal paths they call them, which is one line segment followed by another line segment followed by another line segment. We'll start at a point on C and end at a point on C sub 1. That can be done. Yeah. We would talk about it in depth in a graduate level class, but this level, we'll take that as a kind of a geometric given. The reason they mention polygonal lines, the picture they've drawn is just a single line segment. Yeah, but if the point on C you wanted to start this line segment was somewhere over here, I can draw a straight line segment from this point to C sub 1 because C sub 2 is in the way. We could draw a polygonal path from this point to C sub 1. We go over and down and over some more and then up, and there you go. To weave around the hole that will be punched in that region, C sub 2. So that's the reason they say polygonal paths, yet they've drawn a picture where they've used straight line segments instead of a sequence of straight line segments. Introduce a second polygonal path connecting C1 to C2. In their picture, it can be done with a single line segment. Connect C2 to C3 and so forth, and then connect the last path, C sub n, wasn't it? Connect the last path back to C. So what they're getting at is a picture like this, where they're going to connect the outer simple closed contour to C sub 1 with a polygonal path, and it won't intersect any of the other stuff. That can be done. And then they're going to connect C sub 1 and C sub 2 with a polygonal path. Then they're going to connect C sub 2 to C sub 3 and so forth. And the last one, they're going to connect back to C. Here's what that gives you that's such great news for Cauchy-Gier's thought. They've introduced some more verbiage here. Gamma 1 and gamma 2 as simple closed contours. And we have this function f, analytic inside gamma 1 and gamma 2, and here's what those are. So what we're going to do in their picture is we're taking a piece of contour C, then we're picking up a contour along L1, remember potentially a polygonal path, but anyhow, the picture's clean with straight line segments. We're going along L1 in one direction. Then we're going to go along C sub 1 in its orientation. Then we're going to go along L sub 2 in one direction. And then we're going to go along C sub 2 in its orientation and so forth and connect back to C. So what we've got with this gamma sub 1 is a contour, say, that starts here, oriented in this direction, and you arrive back where you started. So gamma 1 is a simple closed contour. Gamma 2 will take the rest of contour C, will go along C sub 3, go along L sub 3, the last polygonal path, backwards from what we did before. We'll go along C sub 2 in the direction of its orientation. We'll go along L sub 2 backwards. We'll go along C sub 1 in its direction, and then we'll go along L sub 1 backwards, creating gamma 2, which is this simple closed contour. Now, what's going to happen when we set up integrals is we're going to integrate over, say, L sub 1 in one direction, and we're going to integrate over L sub 1 in the opposite direction, also called negative L sub 1. Those two integrals are going to cancel out. So we'll get cancellation of integrals at L1, at L2, and so forth. And we'll be left with an integral around C plus an integral around C sub 1 plus an integral around C sub 2, and so forth. So that's the plan. Those words we're trying to explain this picture. And granted, as I call it a picture proof, and I put proofs in quote marks because this is a little, it's lacking in rigor a little bit. But hey, Cauchy-Gersaw theorem says you integrate around gamma 1 and gamma 2, you're going to get integrals which are 0. Let's go back to that picture again. So we said this function was analytic for this picture, a little figure 8. It was analytic inside C and outside C1, C2, and so forth. So that means it's analytic in this figure 8. Oh, that's the interior of capital gamma 1 and the interior of capital gamma of 2. So that function is analytic inside gamma of 1. Gamma 1's a simple closed curve. Cauchy-Gersaw tells you that integral 0. Integral around gamma 2 is 0 as well. So each of those integrals are 0. We had an analytic function inside gamma 1 and gamma 2, not inside some other stuff, but inside those. So if we add those integrals together, we'll get 0 out as well. So the integral of gamma 1 union gamma 2 of f of z dz is 0. Remember, we're trying to show an integral is 0. It wasn't this integral. Well, maybe it was. Okay. Now we set this up where we cross those little polygonal line segments, the L1, L2, and L3 in the picture. We crossed them in one direction, and then we crossed them in the reverse direction. Well, you know, when we integrate along L in one direction, we get the negative of integrating along L in the opposite direction. Properties of integrals. I guess it was note 4.40.b. So when we go through and integrate around gamma 1 union gamma 2, we're going to get cancellation of those pieces of the integral over L1. We integrate in one direction, we integrate in the other direction, we'll bust the integral about gamma 1 into a bunch of little pieces. There was a piece over C, then there was a piece over L1, and a piece over C sub 1, and a piece over L2, and so forth. Yeah, all the L stuff cancels out when we integrate over gamma sub 2. So we get cancellation of those little pieces. You're left then with the integral around the outside plus the integrals around each of those little constituent simple closed contours. That is the integral of f about c plus the sum of the integral of f about the c sub k's. Add that up, you're going to get 0. Where does 0 come from? Cauchy-Gersaw gave us the 0. Let's look at this one more time. When you integrate around gamma 1, you get C, well, a piece of C. Ooh, you get L1, a piece of C1, L2, a piece of C2, L3. When you integrate around gamma sub 2, you get the rest of C. Ooh, negative L3 in the picture. The rest of C sub 2, negative L2. The rest of C sub 1, negative L1. You get the L's to cancel, you're left with the whole integral about C plus the integrals about C1, C2, and so forth in general. So the picture tells a whole story. The picture and the orientations they put on those contours, that really tells the whole story. All right, let's see what else we got in the notes. Okay. Oh, some complaining. Yeah, interior to a simple closed curve. That's not a rigorously defined definition. We'll be fine. We're just in two dimensions here. Um, two real dimensions, if you like. We're in something that's topologically the same as the Cartesian plane. But there's a lot to the story about saying a simple closed curve has an interior and an exterior. Something called the Jordon curve theorem pops up in topology. I've got some notes posted online, a bunch of notes on topology as of today's date, 2020. I actually don't have things on the separation theorems from chapter 10, but one of these days. But this idea of the interior and the exterior of a simple closed curve is a very surprisingly involved topological concept. How do you know you could do that polygonal line stuff? You actually could connect those things together. That we would explore in graduate complex analysis in this same setting. So it's to be done for this particular result. Check out the notes on connectedness, chapter 2 in the graduate book, so it's coming pretty early on. It's coming in a metric space setting, if memory serves. But there are a number of details to deal with in terms of the quote-unquote proof of that previous result. Some topological, well, actually all of them topological. This is a topological result as well, even though we do it in graduate complex analysis. Now, I ain't that real blown away by theorem 4.49.A. Oh, but I love this guy. Corollary 4.49.B, principle of deformation. Accomplishes a bunch of stuff, and its proof is based on what we just did. It's a corollary to that previous theorem. It says, let C sub 1 and C sub 2 denote positively oriented, both of them positively oriented, simple closed contours, where C sub 1 is interior to C sub 2. If f is a function analytic in the closed region consisting of these contours and the points between them, having one interior to the other, leads us to think in terms of an annulus type thing. It depends on the shapes of the curves. Then the integrals over C1 of f and the integral over C2 of f are the same. So we're getting equality when these contours C sub 1 and C sub 2 are related in a certain way. They call this the principle of deformation. Let's look at a picture and make sense out of that. And let's go through the proof of that one. All right. Here's a plan. Well, here's a picture. The picture is the plan. So we've got C sub 2 positively oriented. We've got C sub 1 interior to C sub 2. And we had the assumption that that function f was analytic on C sub 1 and C sub 2 and analytic at all points between C sub 1 and C sub 2. I could complain about some topological rigor, but the picture will do. So we've got a function that's analytic on the annulus here. And remember, they call this the principle of deformation for the following reasons. Where is this function analytic? On C1, on C2, and all these points in between. So we could continuously deform C sub 2 into C sub 1. We could shrink it down and do that shrinking over a region on which function f is analytic. Where is this function analytic? On a region that would allow me to take C sub 2 and stretch it down, shrink it down till we got C sub 1, or take C sub 1 and stretch it out until we got C sub 2. And imagine that stretching being done over the region where function f is analytic. That's the reason there's so much topology in this stuff. Hidden under this somewhere, believe it or not, even some stuff about group theory. You can associate a group with a surface and you use simple closed contours in a sense. But the idea is we could deform C1 into C2 or C2 into C1 over the region where the function is analytic. That's the reason it's called the principle of deformation. But the claim is integral over these two contours is going to be the same. All right, back to the statement in the previous slide. All right, theorem 4.49.a tells us if we'll integrate around c sub 2 of f of z dz plus the integral around negative c sub 1 of f of z dz, we'll get 0. So here's where we got that outer positively oriented, counterclockwise oriented contour c sub 2. And interior to it, we wanted, in theorem 49.a, we wanted little contours inside that were negatively oriented, that were oriented clockwise. Well, that ain't what we got for c sub 1. C sub 1 is interior to c sub 2, but it goes the wrong way. Well, let's look at negative c sub 1. Then, remember what we had in theorem 4.49.a. We had a big contour on the outside, and on the inside, we had a bunch of little contours. The bunch is just one this time. And those were oriented in the clockwise direction. Yeah, this c sub 1 isn't, but negative c sub 1 would be oriented in the opposite direction, and that would totally fit what we had in that previous theorem. So if we'll integrate over c sub 2 plus an integral over negative c sub 1, we'll get out 0. Well, if we'll move that integral about negative c sub 1 to the other side of the equation, so go back, we left off here. This is exactly what theorem 4.49.a says. All right, we're going to take this term. Remember, it's just a complex number plus a complex number. They're just integrals, definite integrals, because that's the only kind of integrals we've really discussed in here. Take this term to the other side of the equation. We'll have the integral over c sub 2 f of z dz equals a negative of this integral. And that's what we've got here. Oh, but I've got that negative c sub 1 to get the clockwise stuff. Well, we'll replace that with c sub 1. That introduces yet another negative sign. So we lose product of two negatives. We lose the sign out front, and we're left with integral over c sub 2 of f of z is the same as the integral over c sub 1 f of z. It's a picture based on the picture from theorem 49.a, and then it's just a little bit of arithmetic. And it says, back to the notes, it says, dude, you don't have to know very much about c sub 1 and c sub 2. As long as function f is analytic in the right places, you're at liberty to really change contours and not change the values of integrals. In this relationship of deformation, it's more commonly called homotopy. Those two paths are said to be, those two contours are said to be homotopic over the region on which f is analytic. And this can be restated in terms of homotopic contours. More hands-on dealing with the deformation and talk of the deformation. This is a little beyond us at this level, but here's a link to some notes from the graduate version of this class, the graduate-only version of this class. It talks about homotopy and says, we get the integrals to be the same when c sub 1 and c sub 2 are homotopic over the region of analyticity of function f. Well, that's the same thing we just had, ultimately, with some more expensive words. Let's look at C as an example. Any positively oriented, counterclockwise, simple closed contour that goes around 0, with 0 as an interior point. All right, so it could be a unit circle, positively oriented, for example. We're going to evaluate the integral over C of 1 over z dz. We've done this before. We did this. I don't document. Here it is. I guess it was example 42.2. I think we took the contours, say C sub 0, to be, I think it was a circle, a radius 2, if memory serves. We took a circle, that's what it was. We took a circle of radius 2, and we cut it into 2 pieces. We integrated over one piece and the other piece, and then added them together. Because 1 over z doesn't have a nice antiderivative, So we got burdened with logarithms, branches of the logarithms and branch cuts. It's the reason we had to break it into pieces. Anyway, we've done that integral before. We've integrated 1 over z dz around, I think it was a circle of radius 2. We got 2 pi I. Well, the only place this function is not analytic is at 0. It's analytic everywhere except for 0. All right, excellent. Then if we had any simple closed contour, positively oriented, I'm going to have to keep the orientation the same, that goes around 0, then that function f of z is 1 over z would be analytic between, say, that circle of radius 2 and whatever crazy stuff you drew, as long as you went counterclockwise around 0 and created a simple closed contour. Don't go through 0. Keep the same orientation. I don't care what the path is. This previous result, this corollary tells us, well, the integrals will be the same. The integral will still be 2 pi I. So if you've got a positively oriented simple closed contour that goes around 0, you'll get an integral of 1 over z to be 2 pi I. And that's knowing not very much about that simple closed contour. You've put a condition on its orientation. It had to be simple to fit into the realm of discussion here. And then you know the value of the integral is 2 pi I. So this is a real independence of path type results. No matter what sort of contour we had, we get an integral of 2 pi I within some not too obvious constraints and some not too strong constraints either. Same orientation. You reverse the orientation, I'd expect to see some negative signs start coming up. Simple closed contour. Well, yeah, this whole stuff was based on simple closed contours. About 0, what's special about 0? Well, that's where that function is not analytic. 1 over z is not analytic at 0. So yeah, we're getting somewhere now on our knowledge of integrals and how it relates to the topology of the region, whether it's simply connected, when we got lots of integrals around closed contours to be 0, or not simply connected, when, I bet we'd see a lot of this 2 pi I stuff pop up. I mean, there's more involved functions in this, but there's a lot of 2 pi I's that'll pop up in integrals of this sort, where you've integrated around a point of non-analyticity for maybe for an algebraic function at least. On to the next stuff. I'll see you in the next section.